This video explains the design concepts for radar receivers. The requirements for a radar receiver include various specifications that ensure optimal performance and accuracy in detecting and processing radar signals. The conversion of radio frequency signals into video or audio frequencies is essential. Video frequencies are used for imaging radar, while audio frequencies are utilized for measuring speed using the Doppler effect. The radar receiver is intended to amplify the received signal with low noise while preserving its waveform. Optimization of the probability of detection of targets by selecting an appropriate receiver bandwidth, and enabling a wide dynamic range to adjust for small echo signals amid large interference from fixed targets. In the radar receiver, noise and jamming signals are to be suppressed and unwanted echo signals from fixed targets are to be attenuated to optimize the target location. The simplest and most affordable radar modules utilize a direct conversion receiver. The high-frequency received signal is directly converted into a low-frequency baseband signal in this setup. This conversion occurs in a mixer, which uses a portion of the transmitted power as a reference for the incoming signal. The output of the mixer reflects only the Doppler frequency. Mixers typically require a minimum amount of RF power at the input to function properly with the local oscillator frequency. As a result, the transmitter must be capable of supplying twice the minimum required power. The transmitter frequency is characterized by a constant oscillation, which we assume has double the amplitude. The instantaneous input voltage is determined by a time-dependent amplitude multiplied by the phase of the input oscillation during that time. The output signal is the result of multiplying the input voltages. This product can be transformed using trigonometric theorems, resulting in a mixture of upper and lower sidebands. The 1/2 factor here clarifies our assumption of double amplitude at the local oscillator input. This allows us to eliminate the 1/2 factor later on. The upper sideband consists of the sum of frequencies within a range double the transmission frequency. The lower sideband is characterized by the difference in the input frequencies, resulting in an output signal within the baseband. The upper sideband is blocked by the low-pass filter and only the frequency difference is further processed. A direct conversion receiver is very simple in design and therefore very cheap but has poor sensitivity. This is because the flicker noise from the mixer stage occurs within the range of the desired output frequencies and is further amplified significantly. A superheterodyne receiver uses 2 stages of down conversion. The mixing stages are usually referred to as a detector in a radar receiver. The amplification of the receiver essentially occurs in a multi-stage intermediate frequency amplifier. A frequency synthesizer generates 3 different frequencies for this purpose. The transmission frequency, a frequency higher or lower by the intermediate frequency for the first down conversion known as the local oscillator frequency. The intermediate frequency for the second detector. The superheterodyne receiver can be made much more sensitive than was possible with the direct conversion receiver. The flicker noise of the first detector is outside the bandwidth of the bandpass filter. The flicker noise of the second detector is of little significance because the signal strength after the if amplifier is considerably larger. In a mixer, several output frequencies are generated. The amount of the difference between the 2 input frequencies can pass through the filter. However, 2 different received frequencies fulfill the filter condition. One is the received frequency that lies above the oscillator frequency by the if, and the other is the received frequency that lies below the oscillator frequency by the if. However, only one of the frequencies is desired, the other is the unwanted image frequency. The frequency spacing between the 2 frequencies is twice the intermediate frequency. The signals received from the image frequency are added to the signals from the desired received frequency in the receiver. You don't always have to assume strong jamming signals from the image frequency, but at least the additional noise is received. This doubles the received noise and inevitably reduces the receiver sensitivity. The frequency spacing between the two frequencies is equal to twice the intermediate frequency. An image frequency filter is a bandpass filter that narrows the tuning range of the received frequency. This filter is used before the first mixing stage to block additional noise and jamming signals. The bandwidth of the image frequency filter should be slightly smaller than or equal to twice the intermediate frequency. The bandwidth of the image frequency filter must encompass the entire tuning range of the receiver. It's important to note that this bandwidth differs from the receiver bandwidth, which is defined by the bandpass filter for the intermediate frequency located after the first mixing stage. Consequently, there are two conflicting requirements for a receiver: the need for a larger tuning range and the desire for a low intermediate frequency, IF, that serves its purpose effectively. On one hand, the IF should be as low as possible because lower frequencies allow for the design of filters with a steeper slope and greater selectivity. On the other hand, opting for a low IF increases challenges related to image frequency. As a result, selecting the intermediate frequency becomes a compromise. To fulfill both requirements at the same time, there is the concept of a dual conversion superheterodyne receiver. Two different intermediate frequencies are used. The first intermediate frequency offers the possibility of a large tuning range with a good image frequency rejection ratio. The amplifier that follows here does not necessarily have to have a large gain. It is only intended to compensate for the losses that occur in the two mixing stages and the image frequency filter. The first intermediate frequency is calculated in the same way as for a simple superheterodyne receiver. This intermediate frequency has a relatively high value, in the range between 200 and 450 MHz for the image frequency rejection. A lower intermediate frequency is usually adequate for radar systems operating in the L-band, which typically ranges from 1250 to 1350 MHz. In this case, a superheterodyne receiver with only a single down conversion can be used. A radar receiver operating in the S-band, which typically ranges from 2700 to 3200 MHz, requires a higher value. This requires two stages of down conversion. The same principle applies to the second intermediate frequency, but now the input frequency is the relatively constant first intermediate frequency, without a large tuning range. An image frequency cannot exist here. The second intermediate frequency is low enough to ensure an extremely high gain while maintaining the required receiver bandwidth. The third down conversion uses the center frequency of the intermediate frequency amplifier as the local oscillator frequency, a process known as demodulation. The output signal now contains only a video pulse along with its superimposed Doppler frequencies. To receive signals in radar frequencies within the S-band, the receiver needs to operate within a frequency range of 2.7 to 3.3 GHz while avoiding the risk of including an image frequency. Consequently, the first intermediate frequency must exceed 300 MHz. A value of 450 MHz, as referenced here, is sufficiently large for this application. Given these values, the first local oscillator frequency must be tunable between 3.15 and 3.75 GHz. The second intermediate frequency typically ranges from 30 to 75 MHz. This range is often a compromise between simplifying circuit design and ensuring the necessary IF bandwidth to process all components of the transmitted signal. The 75 MHz value mentioned here is based on a real air traffic control radar system. The second local oscillator frequency is a stable, fixed frequency at 525 MHz. The third frequency used for down conversion is the center frequency of the IF amplifier, which is exactly 75 MHz in this case. All of these frequencies required for down conversion, like the transmit frequency, should be generated from a single source with highly precise phase consistency. Only with this level of coherence can the radar effectively measure Doppler frequencies. The receiver sensitivity is often referred to as MDS. The abbreviation stands for a minimum discernible signal for an older analog display or a minimum detectable signal for automatic target recognition. The amplitude of a target should be at least twice as high as the average noise level. MDS is then the power of an echo signal at the input of the receiver that just meets this condition. With very good radar receivers, this MDS can be as low as -113 decibels per milliwatt. In radar receivers, we encounter both extremely weak echo signals, often as low as a few picowatts, and very strong signals from nearby sources that can reach microwatts. This wide range of signal strengths can cause the receiver to saturate. Saturation occurs when the receiver is overdriven, resulting in a distortion of the signal shape. The maximum amplitude and signal edges may no longer maintain the correct ratio. This distortion leads to a loss of information, and a weak echo at the same distance may become undetectable. The range between the maximum sensitivity and saturation point is known as the dynamic range of a receiver. This range is measured in decibels and is ideally as high as possible, typically between 30 and 90 decibels for radar systems. To put this into perspective, a decibel value of 90 decibels signifies a difference in signal strength of 1 to a billion. Amplifiers have a limited maximum output amplitude, which is mainly limited by the supply voltage. Larger input signals then no longer lead to an increase in the output voltage. These signals are limited. In practice, the part of the signal above this is cut off while the receiver is in saturation. This applies to amplifier circuits when the transistor is already fully driven and a further increase in the base current no longer affects the internal resistance of the transistor. The figure shows the characteristic curve of a transistor amplifier in a grounded emitter transistor circuit. Ideally, the input signal should be in the linear part of the input characteristic curve. With a very large input voltage, shown as red sine waves, the peaks of the sine wave are in the nonlinear part of the input characteristic. As a second effect, the amplified peak would be larger than the supply voltage. This means that the peak is not only limited in the amplification but also clipped. This is the effect of saturation of a simple amplifier. There are many of these amplifiers in radar receivers. The effect of saturation is exacerbated because the input signals have a dynamic range of usually more than 40 decibels. The radar has to see very weak echo signals from ultralight aircraft and at the same time deliver an undistorted signal from very large fixed targets to the radar signal processor. A simple selection of well-designed bias voltages cannot control this dynamic range. In radar receivers, therefore, there is a series of measures to control the gain. The most common measures are the logarithmic amplifier and some circuits of sensitivity time controls. All these measures must be well defined so that the radar signal processor can follow the changes in the signal processing. A notable enhancement in dynamics is obtained by employing a logarithmic amplifier as the intermediate frequency amplifier. In a logarithmic amplifier, the amplification factor varies depending on the signal strength at the amplifier's input. The characteristic curve of this amplifier is approximately logarithmic, rather than linear. While this nonlinear behavior can be a disadvantage for highly accurate measurements, making it unsuitable for applications like weather radar, it is beneficial for surveillance radar, which does not require such precise amplitude measurements. The logarithmic amplifier in the picture shows a once common logarithmic amplifier topology. The amplifier consists of a cascade of amplifiers, with each cell having a detector stage with its own threshold. For small signals, this structure simply amplifies. However, as the signal gets larger, a point is reached where the limiting amplifier in the last stage no longer amplifies and instead provides a constant voltage. As the input signal gets larger, the currents of the detector stages are added in resistor Ra. All amplifier stages are designed to amplify small echo signals without reaching saturation. Unlike conventional intermediate frequency amplifiers, the linear amplification range does not terminate at a specific saturation point. As a result, when a larger signal is present, it does not saturate the logarithmic amplifier. Instead, it simply reduces the amplification of a smaller signal that is applied simultaneously. If detectors 2 through 5 were not present, the output voltage would be limited by the saturation point of the last IF stage, as it is in a normal IF section. However, when the last stage of the logarithmic amplifier is saturated, larger signals cause an increase in the output of the penultimate stage. This increase is detected by detector 2 and summed with the output of detector 1. This sum causes the output to increase even though the last stage is saturated. Detector 3 causes the output to continue to increase after the second stage is saturated. The overall gain decreases as each stage saturates, but some degree of gain is still available. Proper selection of the IF stage's gain and saturation points results in an approximately logarithmic response curve. Stages 2 to 6 are in saturation and only provide a square pulse for the high input signal. Only stage 1 amplifies the signal correctly and also provides a current component. The resistor combines all currents into a total current that causes the output voltage to a voltage across the resistor. In this respect, it is a kind of dynamic compression. The output signal is not linear to the input signal. However, the output amplitude is characterized by an approximately logarithmic function. One disadvantage, however, is that the pulse shape is changed by the logarithmic amplifier. A normally steep and linear edge rise is thereby broadened, becomes less steep, and is nonlinear. This property causes a systematic error in the distance measurement. The danger of overloading the receiver with echo signals from the radar's close range area can be reduced by time-dependent gain control, the sensitivity time control, abbreviated to STC. Some manufacturers also call this process gain time control or GTC. Echo signals that arrive at the receiver at the beginning of the receiving time of a pulse period are subject to lower free space attenuation and therefore have a larger amplitude. Echo signals received at the end of a receiving time have a small amplitude because they come from more distant targets. With the STC amplifier, the gain is continuously increased for the receiving time. The amplification factor is therefore time-dependent and, linearly, also distance-dependent. The graphic shows the principle of the gain as a function of time and distance. Depending on the site-dependent fixed target conditions, the STC curve can be approximated to the shape of a third or fourth root. Mathematically ideal would be the course of a fourth root, as the proportionality in the radar basic equation is described. In practice, however, it is usually an E-function from the charging curve of a capacitor. High-end radar receivers designed for measurement purposes utilize a logarithmic amplifier to assess the approximate amplitude range of the echo signal. This information is then used to control a separate linear receiving path through an attenuator. To account for the internal delay introduced by the logarithmic intermediate frequency amplifier and the analog to digital converter, a delay line is implemented. Thanks to extremely fast analog to digital converters that operate at clock rates in the nanosecond range, this delay line can consist of just a few meters of coaxial cable. The radar signal processor also needs this control word for the attenuator to accurately reconstruct the original signal strength. This receiver design can achieve a linear dynamic range of up to 100 decibels. However, one drawback is that the input signal power must be split between the two channels, which decreases sensitivity. As a result, this design is not suitable for military applications. On the other hand, it serves as an ideal solution for civilian weather radar, where maximum range is not as critical. The receiver bandwidth must be at least as wide as the transmitter bandwidth to effectively process the entire transmitted spectrum. If the square pulse only covers half of a fundamental oscillation, the power components located at its edges will be lost. To detect a rectangular pulse using fast Fourier transformation, abbreviated to FFT, the receiver's bandwidth must correspond to the highest significant sine wave frequency component. A higher receiver bandwidth leads to a smaller rise time for the edges of the square wave signal, resulting in steeper edges. Additionally, incorporating the third harmonic produces a sum signal that includes the fundamental frequency, which improves the signal representation compared to using only the fundamental wave. Adding the fifth harmonic to the previous harmonics brings the resulting signal closer to the original square pulse. However, an increase in bandwidth also leads to a higher noise level entering the receiver. Since white noise is distributed independently of frequency, it follows that the broader the frequency range to which the receiver's bandpass filters are tuned, the higher the noise level will be. This results in a lower signal-to-noise ratio and, consequently, decreased sensitivity of the receiver. Therefore, a compromise must be reached. For a short rectangular pulse used as a transmission pulse, the minimum bandwidth must be greater than the reciprocal of the pulse duration. For example, if the pulse duration is 1 microsecond, the reciprocal would be 1 MHz. The fundamental frequency illustrated in the figure includes only 1/2 cycle of the rectangular pulse, which means it provides only half of the required bandwidth. In practical applications, however, the carrier frequency of the radar is affected by Doppler shifts. This needs to be considered when determining the bandwidth. The Doppler frequency must be added to both sides of the bandwidth for targets that are either approaching or departing. For instance, at a radial speed of 1000 meters per second and a carrier frequency of 11 centimeters wavelength, the Doppler frequency shifts to plus or minus 18 kHz. Consequently, instead of having a bandwidth of 1 MHz, with a pulse width of 1 microsecond, the theoretical bandwidth for this case should be 1.036 MHz. If the rectangular pulse is additionally intrapulse modulated, for example, a biphase modulation with a Barker code, then the above applies to the duration of the compressed pulse. The time bandwidth product was introduced to describe the possibilities of pulse compression. It is practically the ratio of the transmitted pulse duration, the large letter t, to the duration of the compressed pulse, tau, and thus identical to the pulse compression rate. In radar systems, values of t times b between 5, as shown in the figure, and 1000 can be achieved. In a digital receiver, a general distinction can be made between the RF assemblies and the digital signal processing. Depending on the frequency band in which the radar operates, the analog-to-digital converter can also be positioned immediately after the first bandpass filter and the first down conversion is then digital. The Nyquist sampling theorem defines the minimum sampling rate for the highest frequency you want to measure. The sampling rate of the analog-to-digital converter must be at least twice as high as the frequency to be processed. And this is easier to achieve at the first intermediate frequency of 200 to 400 MHz than at frequencies in the gigahertz range. The last RF amplifier from the RF assemblies only has to amplify the echo signal to such an extent that the value range of the analog-to-digital converter is well utilized. Further amplification or attenuation can then be achieved in the memory by multiplication by a factor. Such multiplication is not a big digital effort. For example, to multiply by a factor of 2, the entire bit pattern of the signal must simply be shifted 1 bit towards the higher order bits. The digital down conversion does the same as the analog model. Each individual voltage value sampled by the analog-to-digital converter is multiplied by a virtual local oscillator frequency that matches the sampling time exactly, and the result is stored in memory. This local oscillator frequency no longer has to be generated in real form. It is sufficient for the processor to know this frequency and to calculate each of its voltage values at the appropriate sampling rate of the analog-to-digital converter. Directly after the analog-to-digital converter, there is still a fairly high data stream. However, after the digital down conversion, the frequency is at the level of the second intermediate frequency. So only a fraction of the data would be needed to measure the frequencies. For example, if the sampling rate is 400 MHz, but the second intermediate frequency is only 60 MHz, then every sixth value is sufficient for further processing. The values in between can be ignored without loss. The matched filter is mentioned here as an example. How a matched filter works is the subject of a separate video, the link to which is given in the description. Any type of filter can be digitally realized. The advantage is that digital data can be duplicated without loss to feed hundreds of filter types in parallel. Analog filters could not do that. Every split in a power divider would have the power of the input signal. The image was taken from the video matched filter, which is why the abbreviation MF for matched filter is still shown here. A matched filter or a matched receiver would only be possible if the shape of the input signals were known. Unfortunately, with radar, the shape of the signal is not known. Of course, the echo signal should look approximately the same as the transmitted signal. But only approximately. The echo signal is changed in shape by the Doppler frequencies. All these changes contain important information about the target. In principle, a matched receiver for radar does exactly the same as the matched filter for radar. Various parallel channels with different receiver parameters, such as different bandwidths of the second intermediate frequency, provide an optimal signal-to-noise ratio for any of the targets under the given receiving conditions. The signal with the best signal-to-interference plus noise ratio, SINR, is then selected from the parallel results for further processing. I hope you enjoyed this video. You might also like to visit the online version of the radar tutorial. Thank you for watching.